Okay, today I would like to give a talk about lasers and metamaterials, especially negative refractive index materials, and then an inspiration that can be applied for research, and I presume it is possible to make dissertation on this topic, maybe several dissertations. In today's topic, there are some research, but in the microwave region, most of them. In optical region, it would be very interesting. Not only experimental realization, that is rather hard, but also calculations and simulations are also very important in this topic, in my opinion. But before going into the details of my proposition, I would like to give account for two topics. One of them is the lasers. Firstly, let us review lasers. And then let us review negative refractive index materials shortly. And then what the idea is. Lasers are nothing but light amplification by simulated emission of light. Just because the board is not very big, I will just write critical points. So in the lasers, what we have? We have a resonator. The resonator is constrained between two mirrors, and we have a gain medium. In the gain medium, we need some kind of excitation. This excitation can be done by a high voltage, or you can prepare a flash lamp and electromagnetic pulse. Whatever the structure of the excitation, at the end of the excitation, let us presume it is an atomic laser, it can be a molecular laser as well. We have a energy diagram. In this energy diagram, there are some points which are metastable states. In the metastable states, the waiting period of the electrons is at the order of a millisecond, whereas it is at the order of 10 to the power 10 seconds in the other states. So this is a very long period, relatively. When the excitation takes place, you just send electrons to upper levels, and those electrons are coming back, as you expect from the simple panorama. And during the decline, of course, some photons are emitted when electrons are tending to lower energy levels after the excitation. And while the excitation goes on, some of the electrons are coming to this state. This is the metastable state. So these electrons are making a population here. Why? Because the waiting period is much longer. So when the electrons are at a certain population, it is actually the process of population inversion. If we send another photon to initiate the action, this photon causes all these electrons to be declined simultaneously. So these electrons emit photons that are in phase, namely coherent, and at the same time, these photons are in the same wavelength because of the energy is the same. You know, delta E is equal to H delta mu. That is why this is mu, and we satisfy the monochromaticity and coherence. And these angles are placed with the Brewster angle. Brewster angle actually reflects one polarization while absorbs all other polarizations. So these photons are going one side to other side, one side to other side, between the mirrors. It is a resonator, as I have said before. Actually, during this process, assume this single atom, millions of atoms here. So all these photons are playing the role of this photon. That's to say, in the all other atoms of the media, there are some population inversions satisfied because of the excitation. And once these photons are incident, so it becomes a harmonic decline process in all atoms. This is nothing but a growing. In the resonator, the optical information is growing, optical wave is growing between the mirrors, and after a while, one of the mirrors is 100% reflective, while the other is, in some portion, transmissive. For example, 98% reflective, 2% transmissive. So we satisfy the leakage, and the leakage is nothing but the lasing. We satisfy a very special light. Actually, this device is maybe the most strongest application of the quantum mechanics in technology, maybe. It's survives in all branches of our lives, from research to medical applications. We all know all these applications in our life. But whatever the lasing power, we still have research to innovate more. In the electromagnetic spectrum, for example, we don't have gamma ray lasers. There are some certain reasons why we cannot do. And in the powers, we have very big powers to cut metals, etc., etc. In the operations surgery, we have some special lasers. So this technology is advancing very rapidly. Actually, the invention of lasers is the revolution in the nonlinear optics at the same time. These are some brief accounts. Have I missed anything? The simple theory is this. There are lots of atoms and the optical wave grows. More or less in this mechanism, and the situated. Why situated? This situates, and once you obtain the other photons, these photons situates the others. That's why light amplification by situated emission of radiation, and the result is monochromatic, coherent, intense, and very special light. So let us keep this in the first place of the information. The second information comes from the negative refractive index. Assume we have a medium here, eta 1 refractive index, eta 2, and this is our normal. In the conventional and natural refraction, if eta 2 is more dense, once the light comes, it goes in this direction. It closes to normal, but in the right portion. So this is the normal refraction. If it is a negative refractive material, at that time, still close to normal, but from the other side. So this negative refractive index materials are very interesting materials, and you can make special lenses, because if the normal refraction takes place in this fashion, in case of negative refractive index, if your lens is made up of these materials, it refracts very strongly. So some microscopes, that is very strong, or some diverging lens, let's assume. In the diverging lens, if this is the normal case, negative refractive index much more stronger, so some kind of telescopes that are very strong. Perfect lens. There is a presentation of perfect lens that describes the negative refractive indexity and metamaterials with a great detail. So I suggest you to look for this presentation to understand all these details. What is at the back of the philosophy of this idea? Let's go to Maxwell equations. In the third Maxwell equations, we have this one. And in the fourth one, we have mu dot permeability of free space J plus epsilon naught del E over del T. So if you take curl of one of these equations, if we take curl, we take curl of this one as well. So instead of del cross B, just substitute this one, and as a result you get the wave equation. Wave equation is nothing but del square E. Let's write it in the first, let's write it in the one-dimensional form, minus one, mu naught epsilon naught del square E over del T square is equal to 0. So from our previous information, of course, you know, if a wave is traveling, for example, in this direction, classical mechanical wave, the solution is del square F over del x square minus 1 over v square del square F over del t square. From this information, just some correspondence. This is the velocity of the wave. So velocity of the electromagnetic wave in free space, you know, c. So this should be 1 over c square. So 1 over c square is equal to mu naught epsilon naught. So c is nothing but 1 over mu epsilon with the square root in the free space. In addition to these Maxwell equations, if we consider the auxiliary equations, for example, we have the polarization that are the considering all dipoles together and all monopoles all together. This is the magnetization. For these things, we have some kind of extra equations. These equations are displacement vector is nothing but epsilon E or epsilon naught E plus the polarization. In the same fashion, for the magnetic counterpart, B over mu or B over mu naught minus magnetization. In any way, I have erased the Maxwell equation because of the place. If we exploit in a certain material, not free space, of course, there should be effect of polarization. Especially in the optical things, we consider the electromagnetic counterpart, but there are some magnetic effects as well. So if you go on and calculate the wave equation for material, at that time, the previous one was related to the free space. At that time, there should be similar equation, but of course modified because of the polarization and magnetization according to the circumstance. So what we get is the velocity of light in that material, similar to this one. These are mu naught epsilon naught. At that time, that should be related to again 1 over mu epsilon. This time the medium. So refractive index. What is the refractive index? Refractive index is actually the velocity of light in the free space over the velocity of light in the material. So 1 over mu naught epsilon naught and mu epsilon square root. In any way, in the results, that is the case, if we assume free space permittivity and permeability values of free space over the medium is relative permittivity and relative permeability, the refractive index is just the square root of the relative permeability and relative permittivity. So we have a information that is in the square root. Here, the square root can be, for example, the square root of 9. What can be the square root of 9? It can be 3 times 3. So this is one of the root. The other root, minus 3 and minus 3. In the same fashion, we always, at the first glance, interested in the positive roots, but it is possible to minus mu and minus epsilon. If these properties are minus at the same time, it is the negative refractive index. In the presentation of the perfect lens, there are very good explanations of all these stories with detail, and there are some other combinations. For example, this is negative, this is positive, this is positive, and so on. So this is the metamaterial philosophy. So metamaterials are finished, lasers are finished. What is the idea for a possible dissertation? As I have said at the beginning of my talk, this topic is under research. And in the microwave region, there are some certain advances experimentally. In optical regions, there are some certain advances as well. But the thing I tell is not very well studied in the optical region, and it is an amazing and strong perspective, according to my view. What if you put a metamaterial, especially negative refractive index material, into the cavity, so the optical gain takes place in a metamaterial? It will be more efficient. It is the expectation, but it must be calculated. How can we calculate? First of all, we have to get the dispersion relation, and the dispersion relation is this story, a little bit detailed, of course. We have to calculate the dispersion relation from starting with the Maxwell equations. We just get the wave equation. In the wave equation, we have to add the polarization and the magnetization if it is required. Magnetization, of course, not the dominant case in the optical deal, but according to the complexity of the calculation, maybe we can add. So here there will be some other items. It will be an inhomogeneous differential equation. Solve out this differential equation and just attain the refractive index that is depending on the frequency of the things going on in the medium. So from this we can estimate the absorption process, and we can think about the optical gain if the gain material were a negative refractive index one. Again, I am telling, this time, this dissertation proposal is not a unique idea. After my idea, I have searched the internet, and there are some other people who think this, and they are trying to calculate. But I haven't observed any satisfactory result that would give certain quantitative information about what would be the results if you put a negative refractive index material into the optical gain medium of a laser that works in the optical region. Okay, next time, inshallah, I will give another dissertation idea about ferroic materials. Ferroic materials are ferroelectric and ferromagnetic at the same time. This is an idea. It can be studied more. Maybe some other idea may come from start at this point. Thank you.